We want to now look at two jointly distributed discrete random variables. Now, the context here is that so far we've only talked about single random variable, but more often than not, real-world applications involve randomness in more than one phenomenon that are statistically linked to each other. So we need to talk about multiple random variables. So now if we recall that for a single discrete random variable, we have the PMF, which gives us the probability that the random variable capital X takes on value small x. But now for multiple discrete random variables, instead of just the PMF, we have the joint PMF. Now the joint PMF of two discrete random variables X and Y is essentially tells us probability capital X is equal to small x and capital Y is equal to small y. And then here we should recall that we use uppercase letters to denote random variables, i.e. capital X and capital Y, these two discrete random variables whose joint PMF we're looking at, and we use lowercase letters, small x and small y, to represent their values, and the comma here means and or intersection. Now, what does this joint PMF of X and Y tell us? That the individual PMFs of X and Y won't. It tells us the joint behavior of X and Y. So now let's look at two properties of a valid joint PMF of two discrete random variables X and Y. Similar to when we're looking at the PMF of just one discrete random variable, these properties are similar to that. Again, the idea is that each probability in joint PMF is between 0 and 1, just similar to how each probability has to be in the PMF of a single random variable. Second, again, similar to how when you look at the PMF of a single random variable, when you add all the probabilities in joint PMF, they should sum up to 1. We have similar conditions for a valid PMF of a single discrete random variable as well. So similar properties need to hold for the joint PMF of two discrete random variables as well. Now, how do we find probabilities concerning X and Y using the joint PMF? Again, let's recall how do we find the probabilities of a discrete random variable X using the PMF of X, right? We know we sum up the PMF over those values of X, right? Similar to that, to find any probability concerning X and Y, we just sum up the joint PMF over those values of X and Y. Just like for a single random variable X, to find its probabilities using its PMF, we just sum up the PMF of X over those values of X. Similar to that, to find any probability concerning X and Y, using a joint PMF, you just sum up the joint PMF over those values of X and Y. For example, if you want to find the probability X is greater than Y, you just sum up the joint PMF over those values where X is greater than Y. If you want to find the probability X is greater than 1, you just sum up the PMF over those values where X is greater than 1, regardless of what Y is, because there's no condition on Y imposed. To find probability Y is less than 2, you can just sum up the PMF over those values if Y is less than 2, regardless of what X is, because there's no condition imposed on X. So the key is to find any probability concerning X and Y using a joint PMF. You can sum up the joint PMF over those values of X and Y. This can allow you to find probabilities concerning both X and Y. It can allow you to find probabilities concerning just X. It can allow you to find probabilities concerning just Y. So using joint PMF of X and Y, we can answer all probability questions about X and Y. Like we found probability X is greater than Y. We can answer probability questions related to only X, like over here, probability X is greater than 1. We can answer probability questions only related to Y, like here, probability Y is less than 2. We just have to sum up the joint PMF over those values. So you can use the joint PMF of X and Y to answer probability questions about X and Y, only X, only Y. Just sum up the joint PMF over those values.